All right, so let's get started. So the first thing we're gonna talk about is 3.1, which is extrema on an interval, right? So applications of differentiation, extrema on an interval. So we've been working with derivatives. You've been doing the chain rule, product rule, sum and difference rule, power rule, right? So now we want to see like exactly what we can use these things for, right? So let's begin with the definition of an extrema. Okay. So when you have a function, f of x, assuming the function is nice and continuous, right? It's going to wave up and down and do all sorts of things. So this function is going to have maximum values and minimum values, right?
Yeah, it cut out for about 5 seconds.
Oh, okay. Well, what I was saying was that what we're going to focus on is the definition of extrema, which is essentially just the overall maximum or the overall minimum, right?
Okay.
So let's suppose that we have a function f of x, and f of x is defined on an interval. We'll call that interval I. And this interval contains a number c, right? So between the two endpoints of the interval, we have a number c somewhere in the middle. It doesn't have to be exactly in the middle. Okay, so the first thing we're going to look at is a maximum, right? So f of c will be maximum when x is equal to c on the interval I if f of c is greater than all other f of x values for all x and I. Right? So f of c is going to be maximum on I if as long as it's greater than all of the other f of x values for every x value in I. Okay, so that's the first part of what an extrema is, right? The maximum part, right? But an extrema can also be a minimum. Okay, so the definition for a minimum, right? We say f of c is the minimum value of f on the interval I as long as f of c is less than or equal to all values of f of x for all x in I. Okay. So notice that with these two definitions here, right, that means that you can have multiple points where you hit that maximum or minimum because of the symbol of the greater than or equal to and the less than or equal to, right? So, for example, let's say we have this closed interval here. And f of x maybe starts out here, it dips down here, goes up, dips down, and then, comes back up over here, right? So if you look here, let's say c is over here, right? Your f of x value, this is your f of x. You see your f of x comes down to when your x value is equal to c, it comes down to this point. Well, let's just say that point is, I don't know, we'll say it's 2 or something. Right, so f of x is equal to 2 over here. But f of x also equals 2 over here, right? So your minimum can occur at multiple points in that interval. Right? Doesn't really matter. What matters is that f of x value is the minimum, right? 2. So that's why we have the less than or equal to sign here. It's the same reason why we have the greater than or equal to sign here, because f of x might hit that max or minimum multiple times. So does it make sense so far for the definition of extrema?
With extrema, we're looking at like the max or minimum the graph like hits, and the graph can hit the minimum like multiple times. So that's why there's less than or equal to.
Right. That's the purpose of that equal to sign, right? Because if, for
Yeah.
example, the equal to sign wasn't there, let's talk about the minimum here, right? Let's say this was just less than, right?
Mm.
Right. So what that's implying is that f of c is the only minimum value you see, right? And f of x never touches that minimum value ever again, right? But we know
Okay.
realistically that's not what happens. Sometimes you touch that minimum value one time, and the function comes back again and touches that. Like, for example, the sine and cosine graph,
Mm.
right? It touches the minimum multiple times, right? So that's the idea. But just to keep it simple, extrema is just your max and minimum values of f. That's all.
Okay.
Okay. So um the minimum and maximum values of f are the extreme values of f on the interval I. So let's take a couple of examples here. Let's take a look at these and see the different kinds of cases we can have. So let's look at scenario A, right? Scenario A, we have a closed interval from -1 to +2, right? And when we start at -1, you have your f of x value equaling 2 over here, right? But as your f of x moves down here, right, when x goes to 0, you get to a minimum value of f of x equals 1 over here. And then the f of x shoots back up to its maximum value over here, right? So
Yeah.
within this closed interval, right, we have both a maximum and a minimum, right? So f of x is continuous. We have a closed interval, and it turns out that what we end up with is our two extrema, the minimum and the maximum.
Yeah.
Okay, so let's take a look at the case where f of x is still continuous, but the interval is open this time.
Mm.
So look at the difference, right? Since the interval is open, right, left uh, your left endpoint over here, right? Your f of x never gets there because that interval is open, right? So it never gets there, but it does hit that minimum over here, right? So same scenario, it hits the minimum, but now going towards the right, again, that's an open interval. So your f of x never gets there. So we can't even call that a maximum anymore because your f of x doesn't reach it, right? So in a scenario like this where your f is continuous, but the interval is open, you end up with only one minimum, right? So your f is continuous, your interval is open, right? And you ended up with one minimum.
Okay.
Right now, this doesn't mean this is always the case, right? Because it's very possible that you don't end up with any extreme values at all, right? Because if you look here, I can draw a straight line connecting those two endpoints, right? And since this is a straight line function, it's still continuous on that interval. But because of the open endpoints, right, we don't get a minimum anymore. So in this case, there are no extrema. Does that make sense?
So the line you drew, is that
Right.
like does it exist along with the original line?
No,
With
no, no.
the
I'm saying forget this and
Okay.
let's consider, a new function. Because the point I'm
Yeah.
trying to make is that just because the f is continuous and the interval is open doesn't mean that you end up with only one extrema, right?
Mhm.
Because it's also possible that you end up with no extrema at all.
Yeah.
right? And that would be, just to show you an example, that's why I drew this line, right? We'll call this line g of x, right? So for the case of g of x, which happens to be a straight line, you end up getting no maximum or minimum. So there are no extrema.
Okay. And for the last one, even though it's not continuous, we still have an extrema at the endpoints. So it's not defined in the middle. So, well, it's not defined where the minimum is. So we don't have a minimum, even though that is like technically like our lowest point.
Right. Well, yeah, it's not our lowest point because we never get there, right?
Oh, I meant like more so visually
Like,
looking at it, like, yeah.
Yeah, if we were to get there, that would be the lowest point, right?
Yeah.
So what's this saying, right? What is this saying? It's saying that the definition, right, based on the definition of what an extrema is, if we do not satisfy the criteria, right? If we do not meet the criteria says that f must be defined on this interval, right? So if we do not meet that criteria, you see here, right? We can have a discontinuous function when x is equal to 0 over here, right? And we no longer have that minimum anymore. We still have the maximum, right? Because f is nice and defined over there, but over here f is undefined because of that discontinuity. So we can't call that spot a minimum anymore.